Chapter 7 Quantum Theory. You have learned in GenChem that atoms have atomic orbitals, s orbital, p orbital, d orbital, and when atoms combine, they form molecular orbitals. These are all quantum mechanical calculation results. Quantum mechanics describe the behavior of matter and energy on the atomic or subatomic scale. Quantum mechanics is the foundation of all chemistry and biology. It underpins every modern science and technology. Quantum mechanics is the foundation for chemistry, material science, spectroscopy, medicine, many areas. Classical mechanics describe accurately how matter behave at the macroscopic level, such as planets orbiting the sun or ping-pong balls bouncing around in a container. At the atomic and molecular level, nature does not behave in the same way as macroscopic objects, and quantum mechanics is needed. Quantum mechanics is a mathematical description of matter on the atomic scale. Let's first go over some important concepts in classical mechanics. Two distinct types of motion are known in classical mechanics: particle motion and wave motion. Particles are characterized by mass and velocity or momentum. Particle motion is governed by force and Newton's equation. Waves are characterized by frequency or period, wavelength, and amplitude. Wave propagation is governed by wave equation. Here shows some important equations in classical mechanics. Kinetic energy is half mv squared. Momentum is m times v. Newton's law is m times acceleration. Now, because momentum is m times v, so kinetic energy can be also written as momentum squared divided by 2m, p squared divided by 2n. These two equations are equivalent. And the Newton's law, m times a acceleration, and because acceleration is the velocity derivative over time, so the Newton's law can also written as the momentum derivative over time. Rotational motion resembles translational motion, but the mass change to I, the moment inertia, and the v, the linear speed change to angular speed. So rotational angular, the kinetic energy is half I omega squared, and the momentum is I times omega. Newton's law becomes I times angular acceleration. In the next 3 slides, we'll go over the concepts in calculus. In calculus, the derivative is a measurement of how a function y changes when its input x changes. The symbol is dy over dx, or y prime. For example, the derivative of a distance over time, right? The distance over time is the velocity, the instantaneous velocity. The derivative of function equals the slope of the tangent line to the graph of a function at the point. Let's try to derivative 3 functions. The first function is a constant. The derivative should be 0. And the second case, the function is constant times x. The derivative is the constant c. And the third case, the function is constant times x squared. The first derivative is 2 times c times x, and the second derivative is 2 times c. In the first case, the function is constant. If y is a distance, then this is the case when the distance is a constant and the velocity is 0. So if distance doesn't change, there's no speed. In the second case, the derivative is a constant. Derivative is the velocity or speed. So if speed is constant, for example, a vehicle traveling with a constant speed, then the distance will be proportional to time. So the longer time it travels, the more distance it will travel. Okay, so distance is proportional to time. X here is the time. In the third case, this is the case of free falling objects, where the acceleration is constant. Here, the second derivative means acceleration. First derivative is the speed, and the second derivative is acceleration. So acceleration is a constant. So for example, the g is the gravity, is the free falling. That's the acceleration, is a constant 9.8. Okay. Now the second derivative we can written as the first derivative and then derivative of x. So in the next slide, we're going to try second derivative of these two special functions. Let's try first derivative and the second derivative of these two functions. First function, first derivative, sine becomes cosine. And then your derivative Rx becomes R. So the first derivative should be C, constant C times R times cosine Rx. And the second derivative, cosine becomes negative sine. And then your derivative Rx, you get R again. So R, you get R squared. So second derivative should be negative C times R squared times sine Rx. Okay, note that second derivative, you give back to sine Rx. Okay, you start with the sine Rx. After you do second derivative, you get this function back. All right, let's do the next function, C times ERX. The derivative of ERX give you ERX back, but then you derivative RX times R. So that's the first derivative. Now second derivative, again, the ERX give you ERX back, and then you times R again. So R times R give you R squared. So that's the second derivative. Again, after your derivative, you get the function ERX back. The second derivative give back function, the original function ERX. So these two functions are very special in that when you derivative the function, second derivative, you get the function back, all right, times a constant R squared. So in mathematics, this kind of special function is called eigenfunction. Okay, so this is the eigenfunction, and the second derivative in mathematics is called an operator. Okay, the constant. Okay, when you give the function back times the constant, and that constant is called eigenvalue. All right, we'll talk this more about later, because this kind of function is special in quantum mechanics. Suppose we throw an object into the air with initial velocity v0 and angle theta. We can apply Newton's law, F equals ma, and because acceleration is the derivative of velocity or speed over time, we can write Newton's law as m equals dv over dt. But if we know the force, okay, how much force we use to throw the objects and the mass of the objects, we can integrate this equation. We get velocity as a function of time. So we know how fast the object moves at a certain time. Now, because the velocity or speed is the derivative of distance over time, the Newton's law becomes a second derivative of distance over time. If we integrate this equation, we get distance as a function of time. And therefore, we know at any time where is the object and how fast it goes. The fate of this object is determined. And this is very common in classical mechanics. And you will see that in quantum mechanics is very different. What we know in quantum mechanics is the probability. We just went over particle motion in classical mechanics. Now let's look at wave motion. One example is water wave. An example of wave is called a harmonic wave. Harmonic waves are waves with displacement that can be expressed as a sine or cosine function. Wave function is a function of location. X represents location. So at different location, waves have different displacement. Lambda is called wavelength. Wave function is also a function of time. If you choose a particular position, then you will see the wave goes up and down as a function of time. And in this equation, t is the period. And therefore, wave function is a function of location and time combined. Here again shows the wave equation. A wave has some properties that a particle does not have. One of these properties is called diffraction. When a plane wave is blocked by a wall with a hole, this wave can pass through this hole and spread out, and this is called diffraction. Suppose you have a ping pong ball, it can either go through it straight or blocked by the wall. When the wall have two holes, this will form 2 point waves, and the two waves will interfere. Some places they form constructive interference, where the displacements add together, and some places form destructive interference, where the two the displacements cancel each other. Here shows interference between two water waves, and you can see some places water high is very high is due to the constructive interference, and some has no height is due to the destructive interference. The nature of light puzzled scientists for many years. Many scientists believed that light was a particle. This is because when you shine lights on a mirror, it comes back with the same angle. It's like when you throw a ping pong ball on the wall. On 1801, Thomas Young did a double slit experiment and let light go towards a wall with two holes. And what he observed on the screen was a pattern with bright, dark, bright, dark. And this pattern is clearly due to the interference of light. And therefore this experiment confirmed that light is a wave. Okay, because interference is the property of wave. And now we know that light is an electromagnetic wave, and a visible light is only part of it. The speed of light is 3 × 10⁸ meter per second, and the speed is wavelength times frequency.